work that he's done for his thesis for the past couple of years, focusing on the fundamental understanding of electricity and magnetism, in particular the connection between magnetism and electricity, so induction. This is Dustin. So he drove all the way out from Washington State last couple of days. He has 5 kids. They're all rooting for him, I know. And anyway, so without any further ado, Dustin, go ahead and present your work.
Well, I'd like to say I'm appreciative for all the help I've gotten from this school, and I really enjoyed learning and being a student here. And I'd like to present my thesis defense, which is titled with the question. And the question is, will an axial rotated solenoid induce a radial EMF? What that means is you imagine that the magnetic field is rotating with the solenoid, and there's this electric field coming off of it. Okay. This is just an outline. So I'm going to go over the 2 main types of induction that there are, and then I'm going to go over rotating a magnet and the induction that comes from that, but I'll also probably talk a little bit about what happens if you keep the magnet still and rotate the wire. There's a question that inspired the initial investigation, so Dr. Woolley. And so that inspired us to look into this a little more, as well as other experiments that'll be discussed right after this. We have Barnett's experiment, and he was actually trying to answer this question as well. Well, Joseph Tate may not have been trying to answer this question. His inspiration may have been for different reasons than we initially thought, but his test would have been an answer possibly to that question. So we looked into that. And there's also, like I mentioned, a Bartlett and Moore's experiment as well, and they also were trying to confirm Joseph Tate's experiment. And in our experiment, so we deal with we have 2 experiments. One was with a solid magnet, and another one was with an electromagnet, solenoid. And then I go over Purcell's electric field and charge length contraction, and why I think from his theoretical viewpoint, I begin to realize why it's likely that the magnetic field doesn't rotate. And the reason why I go over that is because our experimental results indicated that it didn't rotate axially. Okay, then we go into conclusions for the actually that's reversed now. It's acknowledgments, then the bibliography. Fix that later. Okay, so we have 2 types of induction. I want to make a quote from Richard Feynman, his book. And this is the reference here, and it's in the bibliography. Page 1712, he says, "We begin by making an important point. Part of the EMF that comes from the E field does not depend on the existence of a physical wire as does the V cross B part. The E field can exist in free space, and its line integral around an imaginary line fixed in space is the rate of change of flux of B through that line." So we have perimeter that there's a changing B field. Note that this is quite unlike the E field produced by static charges, for in that case the line integral of V around a closed loop is always 0. So this is be like you integrate around a closed loop for an electric charge, and yeah, that's like around a loop. So with these equations, we get the basics of there's the there's negative dVdt equals the curl E. That's the changing magnetic field. You often get light from that as well. And then you have the V cross B term, where you're moving through a magnetic field and you observe a relativistic electric field. So this leaves us with 2 forms of electromagnetic EMF that have been historically used to either move charge in wire or induce motion by moving charge. So I'm going to go over one concept of magnetic induction, I'm going to discuss when the magnet's rotated. Now, this may not be accurate for rotating a magnet, and more so accurate actually for rotating the coil. But I'm discussing an alternative point of view. You could think of the magnetic field as rotating. So then imagine the magnetic field rotating with the magnet. Now the magnet's actually coming out of the page and it's rotating. So here we have the velocity going into the page. So this is a relative velocity. So if the magnetic field is rotating coming out of the page at us, right, then the wire it sees the magnetic field that's approaching it, right? And so it thinks it has a velocity if the magnetic field is sitting still. The wire thinks it has a velocity towards the magnetic field that's moving towards it. So then the relative velocity of the wire into the page. So then by V cross B, probably should have electric field pointing up here, but then the negative current is down. So, and then on the other side, of course, you have a current force on the negative current, which are the electrons up over here. So that's the concept, and this is realistic, I think, more so when you rotate the coil, more so than the magnet. Okay. Then there's another concept, and this is where you have a radiating change in information. Okay, so basically we have an old magnet in its previous position. You can see that the B field will be pointing down out here. And this would be the position of the old magnetic field. Now you have a new position for the magnet. It's been rotated. Now you can see that at this point, the magnetic field has a downward component that's now smaller. Same out here. It used to be pointing down. Now it's actually a smaller downward component. However, the velocities, the relative velocity here is reversed depending on your position. So if over here, the relative velocity with respect to this changing information is actually inward, and over here is actually the opposite direction. You can imagine the sphere is expanding with the velocity and the speed of light. So then you'd have to overwrite the old information, you would have to overwrite it with a vector pointing up. So I introduce that vector here, dB, relative velocity in, right-hand rule, v, dB, e, pointing out. And this is the same, you get the same induction if you imagine the magnetic field rotating as well, I believe, which is, so you have the magnetic field pointing in, so then, but then your relative velocity would be, I believe, pointing for the wire. Which way is this magnet rotating? It's rotating this way. So then this actually, the magnetic field has velocity up, so your relative velocity would be pointing down if you're a charge in the wire. So you point down, and then you have the B field pointing into the magnet, B cross B, right hand rule, B, B, and again you get the electric field pointing out as well. So it's parallel there. Another interesting thing to note now, this is a radial induction, so it's like changing the magnetic field, dB/dt equals the curl of B. However, we also have, you can also emulate a rotating magnet, right, with, as I put down here, three-phase coils that don't rotate at all. So you don't necessarily have to have a rotating magnet, you can use three-phase coils and do the same thing. All right. So I'll move on from this introduction to it's a form. That's just a mystery to consider. We'll be getting into later, actually. But that's just some basics of induction, what we might see. Okay. So here's a mystery. Now this is the question we asked with respect to the Faraday generator. Now, the mystery is there's a force behind the Faraday generator. Okay, the Faraday generator is a metal disc with a wire connecting its central axis to its edge. This particular Faraday generator I'm going to discuss has a metal disc that rotates with a magnet on the inside. So the magnet's rotating also. All right. Now there's a wire connecting the edge of the disc to the center. So the question is whether or not the magnetic field rotates with this disk. And so the question I wrote down here is the force on the middle disk, is the force in the disk? So is the disk rotating through a non-rotating magnetic field? In which case then the disk is experiencing velocity through this magnetic field and it's experiencing an EMF. Or is the magnetic field rotating with the disk? In which case the disk is sitting still relative to a rotating magnetic field, and it's the connecting wire that's experiencing the EMF. So I'm going to show you a picture of this real quick. Here's the disk. The question is whether or not the magnetic field actually rotates with the disk. And there's a magnet inside this disk. It's coated in metal. We have a sliding contact here and here. We have a voltmeter. But I shouldn't put the voltmeter there. You could put an ammeter there, right? And then we can have current flowing. But if you put a voltmeter there, you'd experience voltage, current trying to flow. All right. All right. So it's difficult to answer both the questions of whether or not the EMF, questions A and B, were whether or not the EMF is in. Whether or not, really the question is whether or not the magnetic field rotates or not. But also, where's the force in the Faraday generator? Is it in the disk or is it in the sliding frame, the sliding wire which resides in the lab frame? So the disk doesn't really reside in the lab frame in my opinion so much because different components of it actually have velocity with respect to the lab frame absorber. Okay, so and I think the problem with it is it's a closed circuit for one, and it has components both in the inertial frame and the lab frame. So it's hard to discern which one's experiencing the relativistic electric field. So Barnett's experiment uses a solution which is to measure voltage induced by a solenoid or capacitor, and it's an open circuit, and it resides in the lab frame. And so he wants to observe this electric field in the lab frame if the magnetic field does rotate. So Barnett measures the voltage after he shorts the capacitor with a wire and rotates the solenoid, unshorts the capacitor and stops the solenoid. So what he does is basically he's rotating this magnet, solenoid, an electromagnet, and then he has an apparatus, and then he closes the capacitor so charge can flow over it, expecting a rotating magnetic field that produces this radial EMF, and it's supposed to cause charge to flow, and then he disconnects it. Now you have stored charge, and he goes back in and measures it. So he did not confirm this. He confirmed it, but they did not see the flow of charge that they were expecting to see. So the electric field he was looking for. He measured the voltage in real time. Okay. By connecting a high resistance voltmeter to the capacitor. This is us. Okay. We do this differently, actually. I want to point this out. We measure the voltage in real time by connecting a high resistance voltmeter to the capacitor. So the charge wants to flow. It's kind of like I was discussing with the ammeter on the rotating disc. And the current wanted to flow through the capacitor, but we were directly observing whether or not there was an electric field there. Barnett's experiment was in 1912. It was on electromagnetic induction and relative motion is the name of the paper. And we have the reference there, number 3. Okay, and it consisted of stationary concentric capacitor inside the rotating solenoid. I discussed that. He used a quadrant electrometer to sense the small amount of charge on the capacitor. That's what he used. The results came out negative for magnetic flux rotation. I may be mistaken, but I do question if Barnett's experiment could have measured a rotating magnetic field. The reason is because the lab frame capacitor, which resides in the lab frame, had an outer shield. If the capacitor were to observe an electric field in the lab frame, then so would the shield, which also resides in the lab frame, and the shield shields the inner capacitor. I would imagine charge would flow to the ground before flowing to the capacitor, possibly. I can't say that for sure because I don't know his exact design. I'll show you the image, and he does have an earth you can see. Try to describe his design. Here's the solenoid, and then on here it's surrounded. It's like a tube, and it's hollow, and it's brass tubing, and it's earthed right here. There's an earth, and here's the key box set up, and basically, and he can zero out the capacitor. So that'd probably be what the earth is for, to try and zero it out. Okay. So what am I trying to get at here? Basically, that was my wording. Was that charge might flow before it flows into the capacitor, it might flow over here. The main thing is that basically what we expect to see from a solenoid is actually a dipole electric field. I'll get into that a little later. If we were to observe a rotating magnetic field, we should see that electric field, and then that dipole electric field would exist in the lab frame actually, and then you would have the shield reacting to that. Set them up on that. Okay. Joseph B. Tate's experiment. These are the two references. This was done in 1968. 1974 was just a touch on his experiment, actually. So his actual thesis was in 1968. And it derived equations for relativistic interaction of electrons that applies to it. He was actually doing it for just charges that approach each other, and observing them, but later on he uses it for the charges going in circular motion around a solenoid. He integrates and then arrives at what seems to be a change in charge for the solenoid for current going around. Different velocities, so the electrons are moving at different velocities with respect to positive charges, and then velocities were squared, so then he spun it up, and then you get increased velocities overall, and the difference between the two squared becomes larger. It appears to get this electric field from charge. It does not conserve flux in all frames, so that's another good point. Purcell has an electric field where you have a charge, and we shouldn't get into this yet, but his flux, he has electric field pancaking where the lines can suddenly become flattened like a pancake, right? It's like something's pressing on it. But his conserves in 3 dimensions. So when, if you had a flat plane here, when it starts pancaking, some of these lines that were like close to the center line could suddenly become pushed out of the dimension of this plane. And so he's conserved flux in even 3 dimensions, whereas I'm not sure Joseph Tate does, because when I integrate it around a sphere, you get a velocity-dependent change in charge of the actual electron. And that would conserve, then his charge no longer conserves flux. But he conducted an experiment and measured a change in charge of the solenoid inside a capacitated box hooked up to a balanced cathode electrometer. And so he had positive results for this. So we imagine if the magnetic field were to rotate in this box that he had, his rotating solenoid. I have an image of this. So we're going to skip through this and get you back to the image. You would imagine that, basically the rotating magnetic field, you imagine V cross B all the way around. There's like an electric field shining off the solenoid. We imagine that you could observe a change in charge inside of the box, so this inspired us that maybe this needs more testing. So he had the slip rings inside of the solenoid, so we could feed it power. He had a battery, he had a timer, he had a motor, and he monitored the voltage, and he measured a change in charge. And this is his equation for change in charge, and these are his coil specifications, and turns on the solenoid, rotations per second, and so let's see here. This is where he starts from, but there's more to his thesis than this. I mean, he has the E.dx integration. This is for a charge, the electric field for it, R prime is actually down here, and there's actually a sign component as well. There's X prime. He introduces all these into this equation, and he ends up getting a phi. And it's like an EMF, change in charge. Later on, he ends up getting the change in charge from that. And, okay, well, we're going to move on, I think. So I went ahead and integrated his electric field. I noticed that his electric field looks like this in his thesis. I noticed a similarity to it in Purcell. Purcell puts it about this form, but it's like to the 3/2 power, if I remember right, accordingly, later on. And but his is of different powers underneath, and this totally changes the velocity dependence of the conservation charge. So it doesn't conserve flux. In fact, when you integrate it, you get this equation here. It's CQ arc sine velocity per c. Anyway, when you do the series expansion, you get the Q per epsilon naught, but you also get additional velocity terms there. So, an experimental paper by Bartlett and Ward is an electron's charge independent of its velocity. So they knew from the get-go what was up, I guess, with Joseph Tate's experiment, and they wanted to investigate that. Is the charge, the electron, really changing in charge? And they attempted to detect a change in charge of a rotating AC-powered solenoid inside a closed capacitor using a locket amplifier. Theirs was a giant sphere. It was a double sphere. And so then they had it inside this. They used the locket amplifier was very sensitive, but their methods they used we didn't really want to use because it seemed like it was canceling out magnetic flux lines, and we really couldn't say whether or not they were rotating or not. So, but they addressed Tate's experiment, and they got negative results. So, better hurt. 2 experiments were conducted that we did. Neodymium magnet, coated magnet. We rotated that, and then we also rotated the solenoid with the central capacitors, both inside and out. We modeled this in CAD, machined it from aluminum with help from Dr. Obergon, engineering, over here at WIU, and we use it. We made a call out of it, and we locked it into University of Wisconsin-Madison's rotating wall. We rotated at 3 high RPM, but they had very fragile bearings made out of ceramic, and with time constraints, we would have to stay there for a while trying to balance that thing. We decided it would be better just to take it back to WIU, which was a shame because we had to cut off the collet we made. But with the help of University of Wisconsin, Doug Gummer, had a friend, Gilbert Clay, and Gildan Incorporated actually helped me cut off this collet part, and they even put in a new cylinder and rebalanced it. It was pretty amazing. Initially, I built an op-amp also as a voltage follower for higher resistance with some help with some parts from Dr. Brian Davies to measure the voltage of these low capacitance capacitors. So they have these giant rings, which I'll show you. They're made out of aluminum, really low capacitance. They don't hold much charge. So at a lower resistance, you'll get charge flowing out those. You need a very high resistance to keep the charge on the capacitors. Okay. So later on, but we discovered Dr. Bowley's Keithley 182 had an op-amp built into it, plenty of resistance. Our results indicated no change in charge for the experiment for the rotating solenoid. So the initial testing of the solenoid, the original solenoid on lathe. Okay, so this is here. Okay, this is what happened when we powered up the solenoid without rotating it. So this was interesting because we would apply a current to just a solenoid sitting there. Okay, here's your solenoid, here's our capacitors. Our capacitors out here and here, and your voltmeters hooked up. This is all just connected. It's like a loop around the whole solenoid. You'd crank up the current and you'd see this EMF just form. And it was just from the formation of the magnetic field, but it would just remain there because you would see the So the voltmeter would jump way up here, and then normally it would, you'd lose charge off the capacitor over time. The capacitor discharging function, right? And you shut the solenoid off, and that thing drops to negative. So it's like there's a pressure there the whole time. I'm not sure I understood that, but let's say it wasn't necessary for me to understand whether or not the magnetic field rotated. Let's see what else is there. It was possible also due to the electric field pancaking. So this is another effect where you have electrons going around in a circle, right? I believe you pancake all the electric fields, but you're pancaking in 3 dimensions, and I have an open-ended capacitor here. So when you start pancaking electric field lines, it's possible that you're shoving electric field lines out the ends of the capacitor that are no longer being applied to the capacitor out here. So that might change the electric flux passing through the capacitor. And I tried to estimate that. It came out, I thought, pretty close, but I didn't feel quite comfortable with some irregularities I was observing in differences of voltage depending on current direction. So anyways, it wasn't necessary past that. I'll probably keep going on this. So what else is there? Current reversal, I just reversed the current on the wire and the power supply. That's all I did. Reduction of current, increase. Yeah. Okay. So here's the first experiment. It's just a rotary tool, a magnet. This is my actual capacitor I developed. Just sprayed styrofoam and some aluminum. That was it. And the voltmeter was actually hooked up to the inner tube, and then there was actually another ring out here, as you can see. Okay, styrofoam blocks were necessary. We tried using wood, and the electrons would actually flow through the wood. So that was not enough resistance there. Styrofoam seemed to work. Okay, so this is the data from the rotary tool experiment. So I'm just rotating a physical magnet. Initially, this is what I see, right? I discharge the capacitor, and that voltmeter would actually charge the capacitor all by itself. But I have the charging function. Of course, you can use the charging function for a capacitor, get the constants out of that, simulate, what a charging capacitor should look like for those data points, and then subtract it out, and then you observe. You can see right when I turn my tool on, the vibrations, and then when I turn my tool off, and then some odd behavior. But basically, what I'm experiencing, what I want to see is when it reaches maximum RPM, rotating magnetic fields should be creating an EMF. And what I expected was like way up here, and it's not there. It's 0.007828 volts. Okay, so that's 0.04, and I see my resolution seems to be pretty good. Here it's not so clear, but you'll see it's more clear on the next page that and it's at a higher, I think it might be at a higher RPM as well. That here I have 2 opposing voltages that I should be seeing. So I should be seeing one negative, one positive by reversing the magnet. And as you can see, this is where I started. There doesn't seem to be a whole lot of reversal going on here in voltage. And there's where I turned it off at, right there and there. And what I should be seeing is like way down here, and then over here I should be seeing something way up here, starting from 0 and then magnet goes up. Okay, same thing here. From 0, when I start the magnet up, it reaches max RPM, I think, pretty rapidly. That's what it's, and not much in the way of voltage. It should be like way up here, and then you should see a voltage like way down here. Some of these spikes were interesting at the very end when you turn it off and you turn the tool off. There might be something to those, but that's not what I'm looking for. I'm looking for a rotating magnetic field. Should be rotating like a magnet. All right. So then this is just a picture real quick of the voltage follower that I worked on for a little bit. We ended up using Dr. Billy's voltmeter. This is just some models that we came up with. This is one model, one of the first models I did. We settled on this with the help of Edita Ezra-Skite and I think Jeffries, and they all helped me out, Mark Ratchett. we settled on this design. We did stress tests on the aluminum, made sure that it wouldn't break before we even started machining. Then we started machining it. We got a aluminum cylinder. Dr. Obregon working with me here. It was a lot of work. And then here we are just machining it. And then the finished product, we started winding wire on there. We had to count how many loops. We ended up figuring that out other ways as well later on. We had to glue that. This is University of Wisconsin-Madison's rotating wall. We actually have it mounted in there. We ended up not doing that. And again, the finished product. This is the, you don't see the outer capacitor, but I later on cut out the two inner aluminum rings and then just had the outer two aluminum rings, or the outer capacitor related in the styrofoam. This is the inner capacitor, the aluminum, and it worked. It held charge. Voltmeter. This is a diagram of our, just the solenoid on the capacitor, and then voltmeter measuring, the voltmeter would be connected to these wires here. But if it was the outer capacitor, it would be connected to there. The power supply had to be connected to slip rings that ran through a pipe through there, and so we could feed power to the solenoid. There was the only way to get power to the solenoid. And again, we didn't see what we were expecting to see if the magnetic field rotated. So we would be seeing like a voltage climb when I turned it on. You'll see